All right, y'all. Today we're going to be talking about Docker and some containers, and I am so excited I can hardly contain myself. So today we're going to start off with what Docker is, what its functions are, and then we're going to talk briefly about exactly how it works, and then I'm going to talk to you about why we might use it, what value it has to us, and the DevOps process. And then finally, I'm going to take you through a really short tutorial on how to actually deploy images from Docker Hub onto a container on a server and have those things running and working. So what is Docker? Well, Docker is a containerization platform designed to streamline the development, deployment, and running of applications. By encapsulating applications and dependencies onto lightweight containers, Docker provides unparalleled versatility. The key strength of Docker lies in its ability to ensure consistency across diverse environments, eliminating the challenges of varying development and production setups. Docker Hub, which acts as a collaboration hub, allows users to seamlessly share, discover, and collaborate on images. Beyond simplicity, Docker optimizes resource utilization for applications, making them more lightweight and efficient. Docker is also the result of open source community collaboration and has seen widespread adoption in DevOps field because of its ability to limit the development and production difficulties and use in building robust CI/CD pipelines. So what is a Docker image? Docker images are standalone executables that encapsulate an application and all of its dependencies. An application has a Docker file, which contains instructions on how to build the images and what all dependencies need to be included on it. Images are built in layers, and each layer corresponds to an instruction on that Docker file, which create a modular and reusable structure to these images. You'll see later in the tutorial when we go to pull an image down, it checks each layer, and layers that aren't changed will remain the same. So the Docker file also includes instructions for configuring the runtime environment and setting up ports and communication, and also defining a working directory for the container. So the resulting image becomes a consistent and encapsulated environment for that application to be. And these images are then pushed to Docker Hub, as you can see in this little visual, where they can be shared. Images can then be pulled from Docker Hub onto machines into a Docker repository where they're stored for deployment. So what is a container? A container is an isolated running environment separate from the host machine that accesses the host resource through the kernel, instead of a guest OS. Containers provide a consistent and isolated environment, ensuring that applications run consistently across different environments from development to production. Containers do not have their own operating systems, nor do they require a hypervisor. Instead, they share the host operating system's kernel, which makes them more lightweight and resource efficient compared to a traditional VM, as well as being much faster to start up. The efficient use of resources allows for running multiple containers on a single host without the overhead of separate OSs. And each container runs on an isolated process from the host system, as well as with its own separated file system defined in the Docker file. And this isolation ensures that dependencies and configurations within the container don't interfere with the host or other containers running on it. So how do these different pieces of Docker work all together? Well, the flow of Docker is pretty simple. An application needs a Docker file that serves instructions on building the image for that application. This image represents the application and all of its dependencies, as well as information about it. And images are published to the Docker Hub, where they can be accessed by the creator and others if they're marked as public. Docker Hub in this scenario works very similar to GitHub, keeping track of versioning and hosting images that can be downloaded by others. After it's been published, images can be pulled into their Docker repo that's set up as part of the installation of Docker and its related packages. Images can be built manually via the command line. We won't be doing that today, though. We're going to be using the Docker Compose package, which uses a compose YML file on our server as a sort of manifest list for images to run and how to set up the containers for them. Each container is effectively its own virtual machine, so they have their own IP address and ports, but again, no operating system. And the compose YML lets us set up these containers with parameters regarding those ports, their addresses, and microservices that we need to connect to those containers, as well as, of course, selecting the image that's actually going to fill it. So, since each container acts as a separate machine for addressing, when we start them, Docker is going to build us a default network bridge which, unless stated otherwise, the default bridge is going to bind the public IP of our server to the IP of our container. And this means that traffic to our server's IP will route to our container via listening ports, and we're going to define these in the Docker YML file. For example, if we have a web app that's going to use HTTP, we can map the local host port 80, which is what the request will actually go through when a request is sent to our server, to the container port 80, so that the container will pick it up and the user will be able to interface with container through our main server's IP. This is the default, and we're going to mess with this a little bit later once we get to the tutorial. So why would we use a container? Well, with no OS, containers take up much less physical space and memory than traditional VM image. You'll see during the tutorial, most of the application images we work with are a file size of a few hundred megabytes compared to gigabytes that a virtual machine could take up, not including the space for the hypervisor to work. They're also isolated to separate user spaces when running, which means that the only content inside of a container is from the image, application code and its dependencies. And then that means that there's no configuration or applications on that container that can interfere with it as if we were going to try to run it on just straight on the host machine. Having no OS also allows the container to access system resources much faster and in a more elastic nature than traditional VMs, which give the application more efficient utilization. You can see in this image here that not only do they not have an operating system, but they also don't have a hypervisor, so the applications are able to talk to the system resources a little bit more directly there with less data pass through. Containers are also very, very quick to start up because you don't have to boot into an OS, and that's part of them being designed to be very easily scalable. Multiple instances of a container can be made from the same image and run simultaneously very, very quickly. And Docker has containers orchestration tools that can manage the deployment and scaling of containers across clusters of machines as well. So them being fast and scalable make them a really great option for a lot of systems like failover systems where if something goes down a new instance needs to be launched very quickly with minimal downtime, or for load balancing as well, since new containers can be started on basically any machine regardless of the underlying hardware. This encapsulation aspect also allows images to be run in containers across different environments consistently, which makes them ideal for DevOps style development, which because it reduces the pain at handoffs. Instead of a full code file, it's just images which run the same no matter what. So there's no, well, it works on my machine kind of drama. Okay, so that's a good point about containers, but why do we use Docker itself? There are other platforms for containerization. Well, there are some benefits to using Docker specifically. To start off with, Docker Hub is an excellent resource full of community projects. And just like GitHub, these projects can range from single pages to operating systems to full stack applications. And Docker Hub also gives lots of inspiration and examples to developers who are looking to browse around and see what they want to do for their next project. On top of that, it also handles version control for us for the images and lets you manage them and the containers that you run on servers directly from the hub, which is very handy. As well as the Docker Hub, Docker is very popular and has a ton of plugins and supporting packages. We're going to be using some of them today, like I mentioned earlier, Docker Compose, as well as Container.io and some others. And these tools give you a wide variety of support for streamlining the Docker process, as you're going to see. And many of the plugins and tools also relate to CI/CD applications and automation, where images can be updated and pulled from the hub automatically and then deployed, and this can be used to very much cut down on deployment time and downtime in between deployments. So what is Docker's place within DevOps? Well, Docker and containerization at large is part of emergent architecture from DevOps, and CI/CD is a major part of the DevOps philosophy. Working in small, valuable batches means pushing changes to production often, and Docker's automation and tools make this a very easy task while offering safe fallbacks just to manage the risk of these changes. So it's very easy with Docker Hub to very quickly spool up a server with an older version of an image just in case something goes wrong during an update. Containerization also offers environmental standardization in the sense that even if the development, testing, and production machine have different hardware and configurations under the hood, the container and image is going to run the same on all of them. A big part as well of DevOps and immersion architecture is microservices, which, to be very brief, are small APIs that handle a small portion of a larger application's process on a separate container. These microservices follow the DevOps idea that systems should be loosely coupled together and the information they share should be abstracted as much as possible. We're going to work with a microservice in the tutorial, and I'm going to show you guys how to launch it using Docker as well as connect the two containers. And the idea behind these microservices is to isolate the services so that changing one doesn't take down the entire application if something goes wrong. It's to isolate those changes. Okay, this is going to be a really quick tutorial on getting these Docker containers to run fully deployed on an Amazon EC2 instance. I've got an Ubuntu server right here spooled up that I just logged into for the first time. So the first thing we're going to do real quick is just make ourselves a user and add our user to the super user list. Alright, and with that user made, we're going to go ahead and switch to it in our home directory and make a scripts folder. Okay, with our users made and us being in the scripts folder, we're going to go ahead and install Docker on this computer. There's a lot of ways to do this, but the easiest way by far, Docker actually provides us a convenient script to just install Docker, its additional packages like Docker IO and Docker Compose and things like that, and set up the repository with the correct keys and everything. So we're going to go ahead and do that. And this is the command to download the script. It's just going to curl from getdocker.com this install docker.sh script. All right, and with that script downloaded, we're going to go ahead and make it runnable. Of course. And with that done, we're going to go ahead and run it. And it'll take a little while to set everything up, but that's okay. Okay, so what we have here is our Docker Hub desktop dashboard, and you can see here the different repository images I've got. I've got Buckstop, I've got Game Microserver, and I've got Test App. These are just images that I've already pushed to the Docker Hub. The first one we're going to deploy is Test App, and then the others a little bit later. Okay, so with Docker and everything installed, we're going to test the installation by trying to run a popular Docker image called Hello World. So it's just going to be sudo and we're going to run this. All right, and what you'll see if you look at this is we got this hello from Docker, which is the output of the image, but when we first ran it, it was unable to find the image Hello World locally, and so Docker actually went out and looked in Docker Hub for it and found it at library Hello World, pulled it down, started up the Docker daemon, and made a new container for it, ran it and executed it just based on us running that command. So Docker and everything works like that. So the next step we have to do is going to be making our Docker Compose file. Remember, we are using the Docker Compose package, which is going to let us make this compose.yml, which is going to act kind of like a list to tell Docker Compose which images to pull in, and how to set up the containers for them. So we're just going to nano in. And the first thing you're going to put at the top is just a version. I'm using 3.4. And it's just structured like this, just headings, and then colons, I mean. So services first, and this is going to be where you put all of the actual containers that you want to fire up. So for us, we've got test app, and the first field in these services is going to be image, which tells it what image to pull from. And it's important you include your Docker username here in the path if that's how it appears in Docker Hub. For me, it does. So there we go. As well as image, you're going to define ports. And like we discussed in the presentation, this is going to map which port on the host machine listens to what port on the container. So for this example, we're going to do 8080, port 80 to port 80. So this is just going to be a rule that any traffic heading towards our IP address, which is 172.31.4142 for the server, over port 80 is just going to immediately map into this container, which is this container is where we're going to be running our web app. So ports. After that, you're going to put in a restart rule, which just tells the condition of when to restart, which is we're going to use unless stopped. So if something happens, the server will always just fire back up unless it's stopped. And that is everything we need on the Compose YML. So we're just going to save this. And from there, we are ready to pull. So we're going to do sudo Docker Compose pull, which is going to look at the Compose YML and pull all of those images that's listed there into our Docker repository that we set up with the convenience script earlier. So you can see it's pulling the layers of test app because, of course, images are made up into layers. Each layer corresponds to a command in the Docker file. So it looks like we've got a pull complete. So the next thing we're going to do is sudo docker compose up d. So compose up is going to actually push these images that were pulled into containers, and d just means we're going to do it detached. So you can see it running, and it builds these default network bridges right here. So from this point, we should be able to just enter in our IP of our container, of our EC2 instance into the browser and see our container, because of course it's over port 80, and port 80 is mapped to port 80 on our container. Okay, and so as you can see here, this is our EC2 IP, and this is our test app right here, hello from the container. So that is working as expected. Now, back in our PuTTY window, we can look at all of the containers that are running currently by sudo docker ps. These are just the running containers, and you can see that we've got one test app. You can see the port bridges over here, and this is cool, but just one web app on a server isn't really using Docker. So what if we want to put another web app on the server? What if that web app has a microservice, for example? So for the next part of this tutorial, I'm actually going to bring in our SE2 project, Buckstop, and its microservice onto this server, and we're going to have them accessible at the same time as test app through different ports. All right, so once you have them published to Docker Hub, it's pretty easy to pull them onto the machine. If you'll remember, the Docker Compose YML acts as sort of like a manifest list of which images to bring in and how to set their containers up. So all we actually have to do is add them to that file and then re-pull them. We're going to sudo back into nano. And we're just going to add past test app. We're going to add the other ones. So first is Buckstop. And because this one has a microservice, we're going to do some things a little bit differently. We have to define an environment for it. And then we're going to go ahead and define ports. And we can't have this one on port 80, of course, so we're actually going to set this one to port 8080 and map that one to our container's port 80. So that way, if any traffic comes over our server's public IP at port 8080, which we can, of course, just define in the browser, it will be mapped to our container's port 80, accessing our web app correctly. Then we're going to do a depends on. Micro. And a restarts. And then finally, we're going to make our microserver, which is going to be called micro. Okay, microserver. So since this one doesn't need any ports, this is the only two things we have to define for micro. Of course, we also need it to be restarted unless it's stopped because Buckstop depends on it. So from here, we're just going to save this, and then should be as simple as pulling again. All right, and you can see where it's pulling Buckstop and the micro by layers, and the test app's already pulled, so we won't do that. And then we're going to go to upd, and we're going to try to launch it. Seems like it's running. And one point of note right here is that if you haven't already, whatever port you defined for the other services, so in our case 8080, you will need to go and add an inbound rule on the Amazon security groups to allow traffic on that port. Okay, so we're here at our main site. This is, of course, the default port for HTTP, which is port 80, and it's on our test app. So we bound our Buckstop to 8080, so we're going to go and try that. And sure enough, here we are, it works. And as you can see, after I log in real quick here and try to play a game, that the author and description of the games are there, which means the microservice is functional and connected. All right, and now back on our instance, we can just check out the containers that we have running and see that we have all three.